Hi guys, and welcome to our last new concept for this unit. We're going to be talking about reaction yields. So before we get to the definition of what a reaction yield is, I want to spend just a little bit of time reflecting on what we've learned this unit and how far we've come, right? So the first concept that we looked at was the idea of molar mass and how to calculate molar mass. Then we looked at how to go from mass to moles and moles to mass. Then we use that to do some stoichiometry, and then we use that to look at the idea of limiting an excess reagent. So really, all of these concepts have built. The idea of molar mass has never gone away. The idea of mass to moles has never gone away. It's going to be the same thing with reaction yields. Reaction yields is really just going to be one big question, taking everything we've known and putting it together. So think of where we ended with limiting reagent. We're just going to add one more layer to that. So you want to make sure you have a really good understanding of those base concepts before you view this lesson. So we're going to do two different examples today. Before we do that, let's talk about what a theoretical yield is. So the definition of a theoretical yield is the amount of product predicted by a stoichiometric calculation. Now, anytime I throw around the word stoichiometry, a lot of the times it can cause a little bit of anxiety. So let's talk again the idea of cookies. So has anyone ever seen in a recipe where it says the word yields, right? So it'll say the word yield. That's actually a chemistry term in a recipe, and it'll say yields a dozen cookies or yields 2 dozen cookies. That's the theoretical yield. That's if you do your recipe perfectly, the exact way that it's said to be done, you should get that many cookies. I don't know about you, but every time I bake, I always end up with like 8 cookies when I'm supposed to have 12. I don't know if that's because I'm eating cookie dough, probably. I don't know if it's because I'm making like monster cookies instead of small cookies. So the idea is that that's how much you should get based off of these calculations, but there's a lot of stuff that could go wrong in between. So the actual yield is exactly what it sounds like. It's how many you actually get. So it's the actual amount of product that you recover. So that's great that the recipe tells me I should be getting 12 cookies. I'm only getting 8 at best. So that's your measured value in a reaction. So there's two different values here. One that we're going to be calculating using stoichiometry. That calculated value is going to be a theoretical yield in a perfect world. And the actual yield is when you're in the lab or when you're in the kitchen. How many are you actually getting? So that number's got to be determined by doing. Now that we understand the difference between them, let's talk about why there's a difference, right? Why am I not getting those 12 cookies that I should be getting? There's a couple different factors. First thing I want to talk about is this idea of a competing reaction. So oftentimes, even though we're just looking at one chemical reaction, in grade 12, we're going to start showing you that more often than not, there's not just one chemical reaction going on in a test tube. There's multiple stuff going on behind the scenes. We focus on one because it's easier, but there's actually a lot of chemical reactions that might be happening at one time. These are the idea of competing reactions. So we've actually given you an example for propane here, if you want to look on your screen, and you can see that at the same time, there's both incomplete and complete combustion. This is an example of a competing reaction. So if you're trying to measure the amount of carbon dioxide produced, you might get a lower number than you expect because some of that carbon is actually going towards forming carbon monoxide. So as much as I might want to make sure that all my cookie batter turns into cookies, sometimes some of that cookie batter turns into a snack for me, right? As much as I might have one bag of chocolate chips and they're supposed to all go into the cookies, sometimes I eat a few along the way, or sometimes one of my eggs is smaller than the other. So that's the idea of the fact of a competing reaction, right? You might not end up with as much as you thought you were going to because something else is happening along the way. A competing reaction can also involve the products of the principal reaction. So sometimes what can happen is you can have your products from your first reaction might go on and form something else. There's a few other factors that might affect percent yield. So again, this is just trying to explain in chemistry terms why we might not get a perfect answer or exactly what we're looking for. Sometimes you might have a solubility issue. So sometimes you might have a remaining precipitate and you don't actually get to retrieve all that precipitate. Sometimes you might have products cling to glassware. Hopefully we can do our percent yield lab. It's a great one. Normally in class you'd be making chalk, and that chalk is actually really hard to get off the glass stir rod. So afterwards, your glass stir rod would still appear to be white because a lot of that product is clinging to glassware. Sometimes your reactants aren't as pure as you think they're going to be. So for example, when we say we're using acetic acid, we're really using vinegar in class, where vinegar, the table vinegar that you use is actually only 5% acetic acid, the rest of it is water. So it's really not as pure. Or reaction rate. Sometimes if it's a slower reaction, we might be stopping the reaction before it's actually completed. We'll talk about reaction rate more in grade 12. Okay, so now that we understand what percent yield is and why we might not get that perfect number, let's take a look at how to calculate percent yield. So here's the formula for percent yield. It's the actual yield divided by the theoretical yield times 100. I always say that students are actually great at calculating this because this is how you calculate what you would have gotten on a test in a percent. Your actual yield is actually what you got on your test. Your theoretical yield is how you could have gotten perfect or what the test is out of. So in order to calculate percentage yield, you're going to take actually what you got, you're going to divide it by a potential perfect score, times by 100, and that's going to give you your percent yield. Sometimes you're going to get a 98% yield saying you did really great. Sometimes you're going to get a 30% yield saying maybe your lab was not as successful as you thought through maybe no fault of your own. So we're going to be looking at this example today. This is going to be our one of two examples that we're going to be looking at. We're going to be looking at the fermentation of glucose. So if you take a look, we've been given a couple bits of information. We've been given the actual chemical reaction here. Notice that it is already balanced, and we were given a mass of glucose, and we were given a mass of ethanol, but I'm actually going to highlight a separate word there. So let's read this question together. I'm going to read the second part of the paragraph first. If 20.0 grams of glucose reacts, but only 1.4 grams of ethanol is produced, what is your percent yield of the reaction? So what we've been given here is two masses. The mass of my glucose is how much glucose actually went in to the reaction. And the mass of ethanol, 1.4 grams of ethanol is produced. That's how much after doing the lab I actually got. So that is my actual yields. So what we're going to be doing in this question is we're going to have to use stoichiometry to calculate theoretical yields. And then we're going to compare that theoretical yield to the actual yield that was given to us in a question. So you're going to find that in the percent yield questions, you're always going to be given your actual yield. It's going to say in a lab, you made this much. That's your actual yield. Be careful to not use that in your stoichiometric calculation. So we're going to look at two different ways to solve this. The first way we're going to look at to solve this is the way that we've been really doing it so far. It's going to be that multi-step method. So we're going to look at our molar masses. We're going to determine the theoretical yield using our mole ratio. We're going to determine the actual yield of the product, and we're going to calculate percent yields. So I just want to remind you of the steps that we're going to be doing as we go through. So this is a great summary, but I'm going to remind you that essentially what we're going to be doing is we're going to go from mass to moles. We're going to use that molar ratio. And then we're going to go from our moles back to our mass. So those are always going to be our three steps that we're going to be looking for. So these are the steps we're now great. We're just going to be coming back to that mass to moles, molar ratio, moles to mass idea as we go through. So first thing we want to do is write down our given information. The first thing we were given is our chemical equation, and we're going to check to make sure it's balanced. I see there's coefficients in there, so yes, we do know that it's balanced. So our next step is going to be to write down anything that was given. So all my given information I've recorded here. Really the only bit of information that was given to me was my mass of glucose, which was 20 grams. Notice that I didn't record my mass of ethanol that was given to me. That's because that was my actual yield. I'm looking to calculate my theoretical yield. So don't sub that in by mistake. You want to look at how much you should have gotten in a perfect world. So I was given information about glucose and I'm looking for information about ethanol. So these are the two things that I'm going to be focusing on in this case. So I can essentially go ahead and ignore carbon dioxide at this point. Next step that I want to do is I know that I have to go from mass to moles. In order to do that, I need to figure out my molar mass. So I'm going to look at my molar mass of glucose, and while I'm here, I might as well figure out what my molar mass of ethanol is. So in order to do that, my molar mass for glucose, I'm going to take my mass of 6 carbons. This is carbons. Why? Because I have 6 carbons. And I'm going to add to it 12 times my mass of, this is my mass of hydrogen. Why? Because I have 12 hydrogens. And then I'm going to add to it 6 times my mass of oxygen. That's going to give me a grand total of 180.156 grams per mole. Well, in here, I'm also going to calculate ethanol. So in ethanol, I have 2 carbons. This is your molar mass for carbon. I have 5 hydrogens. So this is your molar mass for hydrogen. I have 1 oxygen, and I have 1 more hydrogen at the end. So if you chose to include hydrogen over here and multiply by 6, that's also okay. You're going to end up with the same number, and the number that you're going to end up with is 46.069 grams per mole. All right, now I have my masses. Now I've calculated my molar mass. So I'm ready for my first step. And remember, my first step is going to be taking my mass and going to moles. So in order to take my mass and go to moles, I need 2 pieces of information. I need my mass and I need my molar mass. I have both of those. So in order to go from moles to mass, I'm going to take my mass and I'm going to divide by molar mass. When I plug my numbers in, that's going to look like this, 20 divided by 180.156. And I'm going to find that I end up with this number here. I'm going to keep as many decimals as possible. The more decimals I keep, the more accurate my number is going to be. When I did this, you're going to note that grams actually would have canceled out, and that mole would have flipped to the top of the fraction. All right, so now I've done mass to moles. Now my next step is going to be that molar ratio. Remember, my molar ratio is going to be set up between glucose, that's where I'm starting, and I want to go to ethanol. That's where I want to end up. So those are the two that I'm going to focus on for my molar ratio. So I started by stating how many moles of glucose I had. I knew this. I calculated it in my last question. So I'm going to call this my moles of glucose. Now what I'm looking for is my moles of ethanol. So I'm going to go ahead and I'm going to call that X. Next thing I want to do is I want to look at my coefficients that are in front of my balanced chemical reaction. So if I look in front of glucose, I have no number written. So we assume that's a 1. And if I look in front of ethanol, I have a 2 written. So I'm going to record this 2 right here. My next step is to cross multiply. So I'm going to go through and I'm going to multiply everything by what's across from it. That's going to look like this. I'm going to end up with X moles of ethanol. I've actually taken this one step further because I'm assuming that you guys are getting really good at this. And I've gone ahead to get my X by itself. I've also divided by glucose at the same time. My top part of my fraction is going to stay the same. So I'm still going to have my number of moles of glucose. I'm going to be multiplying by my moles of ethanol. If I set this up correctly, I should find that I go ahead and I cancel out my units. So I'm going to find that I'm dividing by glucose. Therefore, my glucoses are going to cancel out, and I'm going to be left with just ethanol, which is what I'm looking for in the first place. So if I take that nice big long decimal there and I multiply it by 2, I'm going to find that overall, my number of moles of ethanol, because that's what I was left with, was ethanol, is 0.22202, etc. So let's recap my steps again. I went from mass to moles. I did my molar ratio. So the last thing I'm left to do is to go from moles to mass, which is exactly what I want to do. I need to go from my number of moles of ethanol to my mass of ethanol. In order to do that, I need 2 pieces of information. I need my number of moles of ethanol, which I have. I need my molar mass of ethanol, which I calculated at the beginning. So I'm going to go ahead and take my number of moles, and I'm going to multiply by my molar mass. So in order to figure out my mass of ethanol, I'm going to take my number of moles, multiply by my molar mass, and I'm going to get this number here. Notice if I've done this correctly, I go ahead and I cancel out my moles, right? This mole here was canceled out. This mole here was canceled out, and I'm left with a number of just 10.22869.069 grams. At the end, we don't want to carry this many decimals. We kept this many decimals as we went through to be as accurate as possible, but really what I want to do is I want to round to my correct number of significant digits. I was given one significant digit in this question, 20.0, so I'm going to want to round to one decimal. So my actual number that I would do if I was stopping here, I would round to 10.2 grams. Notice that we're not quite done yet. The whole question was asking for the percent yields, right? And just a reminder of what my formula is for percent yield. My formula for percent yield is my actual yields divided by my theoretical yield. So my actual yield is what I actually got in the lab. My theoretical yield is what I should have gotten in my lab. So if you go back and read your original question, you were told that when you did this lab, you got 1.4 grams of ethanol. So my actual yield, what I actually got was given to me in words. That was 1.4. That whole calculation we just did was our theoretical yields. Our theoretical yields, 10.22, that really big long number. You could actually choose to put your rounded number in here. You're going to find that for this one, it actually doesn't give you a different answer. You could have rounded before. We want to make sure that by the end, we're at least rounding to that one decimal point. The last thing we want to do is we want to multiply by 100. Why are we multiplying by 100? Because again, we're looking for percent. So 1.4 divided by 10.2, that's going to give you a decimal. We don't want to express this in decimals. We want to express this in percents. So that's where I'm multiplying by 100. If I plug that all into my calculator, I'm going to find that I get this grand number here. And like I mentioned in the previous slide, you want to make sure that you are rounding to your correct number of significant digits. That's one decimal. So I want to round to 13.7%. So not a really efficient lab. So something's gone wrong. Maybe there's a competing reaction. Maybe you had a solubility issue, but really you only made 13.7% of the ethanol that you could have made. So that will always work for you. Notice that most of that was actually stoichiometry. So the hardest part of that question was stoichiometry. The actual percent yield part wasn't that challenging. So this is just a chance for you to go through and to practice more stoichiometry. I want to take a look at dimensional analysis now. We call that the one-line method. So I want to show you how you can actually go through and solve this using one line, and then we'll take a look at another example. So your one-line method, again, you're going to go through and you're going to use your units to go ahead and cancel out. So our unit that we're trying to end up with in this case is going to be that mass or that actual, that theoretical yield that we're looking for. So we're going to take a look at what information we were given, but this time we're going to focus on the units. So we were given 20 grams of glucose. We figured out that we have 180.156 grams per mole of glucose. We figured out the molar mass of ethanol to be 46.069, and again, grams per mole. So we're going to use these units to go through and to figure out what to write and what to cancel out. So for our theoretical yield, this is what we're looking for overall. And remember, we're looking for our theoretical yield of ethanol. So we want to focus on ethanol, and we need to use our information about glucose to get there. So we are going to start with the first piece of information we were given, and that is our 20 grams of glucose. So we have a couple different things that we want to cancel out here. One of the first things that we want to cancel out is, since grams of glucose is not in our given value that we're going to be looking for, we want to look at getting rid of that unit. In order to get rid of that grams of glucose, what I want to do is I want to put grams of glucose in the bottom part of my fraction here, in order to cancel out? Well, where's the only thing that I see grams of glucose? In my molar mass. So I'm actually going to put my molar mass in my bottom part of my fraction. That's going to leave me with my moles of glucose in the top part of my fraction. So I've got one of my things canceled out. Now, if you take a look at my answer though, moles of glucose is actually not in my answer either. So I need to go ahead and I need to figure out how to cancel out those moles of glucose. In order to do that, I'm going to use my molar ratio. So my molar ratio, I need to go ahead and I want to put moles of glucose at the bottom here. And for my molar ratio, I'm going to take a look at what number I have in front of glucose. There's no number written, so we go ahead and we assume it's a 1. On the top part, I have the second part of my ratio, and that's going to be moles of ethanol. So if I take a look in front of my molar ratio here, I see a 2 moles of ethanol. So I've gone ahead and I've canceled out moles of glucose, that's good, but I still have moles of ethanol left, which is also not in my final answer. So now I need to go ahead and figure out how to cancel out those moles of ethanol. So the only other place that I see moles of ethanol is in this molar mass here. So I'm going to go ahead and I'm going to write moles of ethanol in the bottom part of my fraction here. By writing my moles of ethanol in the bottom part of my fraction, the top part of my fraction is going to be this number here, this molar mass, this grams of ethanol. So if I go through and I actually punch that into my calculator, 20 divided by 180.156 times 2 times 46.069, I'm going to get this number here. And this number here is my theoretical yield of ethanol. In order to solve this, remember I'm looking for my percent yield. So my percent yield would be my actual yield divided by my theoretical yield, and I'm going to get the exact same value. So you actually have a choice to do that multi-step method that we did for the first part. If that makes more sense to you, if you like following steps, that totally works. Or you have a chance for if you want to get everything over with one line, you can do that one line method using units as well too. That's always going to work, whatever you prefer to do. Let's take a look at one more question. So we're going to do one more question to practice it. Now that last question, that was essentially one of the hardest questions I can give you. I could have thrown in a limiting reagent there, and that would have been one question that actually tests our entire unit. So that's a great gauge for you of do you understand this? So I'm going to show you the next question. If you're understanding this, pause the video, try the next question yourself. If you're not understanding this, then follow me, but please at least once we maybe set up the question, pause it for a second, see if you can figure it out, because the best way that you can actually practice this is by trying it yourself. So we're going to be calculating the actual yields using our percentage yields, and we're going to be looking at this chemical reaction here. So we're going to be looking at ammonia coming together with nitric acid to form ammonium nitrate, which is used in fertilizer. We've been given this value here, so 4.95 kilograms of ammonia gas. What mass in grams of ammonium nitrate is produced if the reaction only is 89.5% efficient. So you're going to notice that we've been given a slightly different value, but our steps are actually going to be very similar. So we were actually given a starting value to allow us to do the stoichiometry. So we're still going to go through with our mass to moles, our molar ratio, our moles to mass. That's the hardest part of this question. And then at the end, we're actually going to be trying to figure out actual yields rather than percent yields. So that last step in the last question, we were figuring out percent yields. In this step, we're just going to be figuring out actual yields. So 95% of my question is still going to be the same. One thing that I'm hoping that you noticed here is we have an unfamiliar unit, 4.95 kilograms. Now we have to be very careful because our units always have to match. Remember that when we're looking at molar mass, we're looking at grams per mole. So we're dealing in moles. So we actually can't use this value of kilograms. We're going to have to go through and we're going to have to convert. So let's list our chemical reaction and let's go ahead and check and say, is this balanced? So if you actually go through and add these values up yourself, you're going to find that they are balanced. So we can go ahead and list our given values. Before we lift our given values, we do want to convert from kilograms to grams. A kilo means 1,000. So to convert from kilograms to grams, we're just going to multiply by 1,000, and that's going to give us 4,950 grams of NH3 ammonia. So we now have our step one, we've converted. Now we need to go through and we need to use stoichiometry to figure out our theoretical yield of ammonium nitrate. Let's write down what we've been given. So we were given our mass of ammonium. Notice that I did record this in grams, and we are looking for ammonium nitrate. So these are the two values that we're going to be focusing on. We're going to be starting at NH3 on the left-hand side, and we're going to be looking to end up at NH4NO3 ammonium nitrate on the right-hand side. I'm going to need molar masses of each, so I've gone through and I've calculated them. So for NH3, I've taken the mass of nitrogen, and I'm adding to it 3 times the mass of hydrogen. That's going to give me this value here. And for NH4NO3, I'm taking the mass of 2 nitrogens, 4 hydrogens, and 3 oxygens. That's going to add to 80.043, and I'm looking for number of moles of each. I now have enough information to figure out my number of moles of NH3, which is what I'm going to do. So in order to figure out number of moles, I'm going to take mass and I'm going to divide by molar mass. So I'm going to take 4,950. I'm going to divide by 17.031. And if I do this correctly, I'm actually going to have it so my units are going to cancel out. So grams are canceling, and that mole is going to flip to the top part of my fraction. So that's going to look like this. I've got 290 that big long decimal moles. This is the plus of actually using that one line method, is you're not dealing with these decimals. You don't have to worry about carrying these decimals over. And remember, you want to carry as many decimals as possible when you're doing the question to have your most accurate answer. So we've now done step one. Step one is to go from mass to moles. My next step is going to be that molar ratio. And remember, it's my molar ratio between my reactant and my product. So those are going to be the two things that I focus on. So in order to set up that molar ratio, it's going to look like this. I've taken my number of moles of ammonium, and I'm calling ammonium nitrate X because that's what I'm interested in finding. I then go back to my balanced chemical equation and notice that it's a 1, and notice that it's a 1 in front of each of them. So I'm going to call this 1. I'm going to call this 1. Next step is to go through and to cross multiply. And just to save us some time here, in one line, I'm also going to isolate for X. So that's going to look like this. I've gone through, I've cross multiplied X times 1 mole of NH3, and then 290.6 times 1 mole of ammonium nitrate. And then to get X by itself, I'm going to bring that mole of ammonium nitrate to the other side. So we're going to cross multiply. Once we cross multiply, this is going to be the top part of my fraction here. Oh my goodness. This is going to be my top part of my fraction. Nope, don't want to save that. I want to cancel that. One more time. There we go. This is going to be my top part of my fraction here. And this, I'm dividing by this to get that mole of ammonium nitrate by itself. What you might have noticed before we did this, though, is that this is a 1 and this is a 1. We call that a 1-to-1 molar ratio. So it's great to follow through with this step, but what we're going to actually find is that our final answer in a 1-to-1 ratio is actually going to be the same. So if you notice that, you don't actually have to show me your work in this step. It's great to show me that you know how to do the molar ratio, but anytime that you have two fractions that are the same on top of each other, your starting number, which was here, and your ending number are going to actually be the same. So we've done our mass to moles. We've done our molar ratio. So our last step that we're going to do is we are going to go from moles to mass. So this is the information that we have now. Our whole end goal is we want to find the mass of ammonium nitrate. In order to do that, we need the number of moles, which we just calculated, and we need the molar mass, which we've calculated at the beginning. So to find this, we are going to take our molar mass and we're going to multiply by the number of moles. We have both of those values. So I'm going to go ahead and plug these in. I have my molar mass. I have my number of moles. And if I do this correctly, I'm going to find that moles and moles actually cancel out. I'm going to be left with just the value of grams. This here is my theoretical yield. So in a perfect world, this is how much ammonium nitrate I should get. Remember what the question was asking for. So the question this time was asking for the actual yields, and it gave us the percent yield. So how does that look different? It looks different this way. So the question gave us this, and we just calculated this. So what we're going to be looking for is this. We're going to be looking for our actual yields. So if we go ahead and we rearrange our equation, we get actual yield by itself. We are going to move theoretical yield over. So we're going to take theoretical yield. We're going to move it over to this side here. That means you're going to be multiplying by theoretical yields. And when I go ahead and I'm multiplying by 100 on one side, so that means I want to divide by 100 on the other side. Now I've got percent yield. It was given to me in the question. Now I've got theoretical yield. I just calculated that. So all I have left to do is to plug in my numbers. I have my percent yields. I'm multiplying by my theoretical yield. That's my calculated value I just calculated. I divide by 100, and I'm going to find that overall, my actual yield is one really big, large number. It's actually 20,821.4. So we can actually use scientific notation to represent this. To use scientific notation, remember, I want to end up with my decimal. Let's actually use my darker one here. I want to end up with my decimal point here between my first and my second value. They're really thick so you guys can see. I want to end up with my decimal point here between my first and my second value. In order to do that, I'm moving 1, 2, 3, 4 different times. So my total value is going to end up as 2.08 times 10 to the 4. That 10 to the 4 is because my decimal had to move 4 times grams of ammonium nitrate. Are we surprised that this is such a big number? Well, not really, because remember, I was given a big starting number. My big starting number was in kilograms, so I'm actually not surprised that I have so many grams. So that would be our final answer, and I do have my correct number of significant digits. So if you want to go ahead, try these homework answers. Remember, we actually have the McGraw-Hill textbook, so we're not worrying about Nelson anymore. We're online only with McGraw-Hill, so we don't need this anymore. So your homework questions are going to be here. Now, these are longer questions because they have all that stoichiometry in them. Remember, homework is just meant for you to practice what you feel you need to practice. So if you do one of these questions and feel confident, great, then go ahead and end. If you're not quite confident, try 2. And if you're really stuck, try 3. There is full solutions posted for these homework questions as well, too. That is it. You are done stoichiometry. I have now taught you everything there is to know about stoichiometry. So please contact me if you have any questions, and good luck in your end of unit assessment. We'll see you later, guys. Bye.